Welcome back to the classroom. Mr. Wong speaking here. We're going to be talking about naming ionic compounds. We have two different types of elements. Now just remember, ionic compounds is a combination of cations and anions added together, being that cations are metals, so metals that have lost electrons, and anions as nonmetals that have gained electrons. If you're talking about in terms of valency, if you've lost electrons, you have increased the positive charge. If you are an anion and you've gained electrons, you've increased the negative charge. In terms of naming ionic compounds, remember the cation will always have the same name. The anion will have a name change, usually by changing it to IDE with the last few letters. Okay, now it's really crucial when you name ionic compounds that you have your periodic table in front of you and you know what the charged values of each one is. So if you just have a look at our chart here, we have group 1, 2, 13, 14, 15, 16, 17, 18. Now, in some cases, sometimes we even call it group 3, 4, 5, 6, 7, 8. The reason being is when we're looking at valence electrons, we have a maximum of 2. So 2 max valence electrons here. We have 8 max valence electrons if we're in the second row. And we have 8 max valence electrons, our assumption that is, for this third row here. Okay, so that kind of gives us a little bit of detail. Anything in group 1, the concept of forming ions is to provide greater stability. Okay, so in group 1, we usually only have one valence electron, which means that in order to get a full outer shell, group 1 tends to lose one electron in order to obtain a full outer shell similar to its whatever group 8 constituents. So what you see here, lithium plus, that implies that we have lost one electron. That's what the plus sign represents. Magnesium 2 plus implies that we've lost two lost electrons. Okay, so if you do have a physical copy of the periodic table, my suggestion is you should try and write it down, maybe on top. Group 3 is plus 3, group 4, don't need to worry about that. We generally don't use group 4s with ionic compounds anyways. Group 5, 3 minus, oxygen, group 6, 2 minus, and then fluorine, 1 minus there. Okay? So you can actually see when we change the atom into an ion, the metals don't have a name change. They are literally the same name as before. You might want to suggest that it is an ion, so you could say instead of a lithium atom, you might say a lithium ion, barium ion, something like that. When we come to the formation of nonmetals, however, we do get a slight name change. Okay, you can see that depending on which group they are, there is a slight difference in the amount of electrons they gain. But essentially we've replaced all the last 3 letters of the nonmetals and added IDE. So what example do we have? Let's use oxygen for an example. The name of oxide as an ion or as an atom is oxygen. The name of nitride as an atom is nitrogen. So you can see you've essentially taken the last couple of letters off the names of these atoms and just added IDE. So that's kind of the crucial point when you're naming anions, is to add that IDE. Okay, so if we're talking about the naming of these ions, these are all majority metals. So let's use aluminium, for example. It's just an aluminium ion. If you combine it together, you can just write aluminium, doesn't really matter. We have sulfur, which is a non-metal, so we call it sulfide. Chlorine would be called chloride. And same idea there. Okay, so that's what we're looking into. Solutions right there. When it comes to naming the ionic compound, again, it's very straightforward. Same idea here. The metal name comes first, so you always write the cation name first, or the metal you might like to call, and then the ion name will come second, which is going to be your non-metal. Okay, remember, metals don't change the names, non-metals you do change the names, and so you get something like this: sodium and chloride, it becomes sodium chloride. Potassium and sulfur becomes potassium sulfide. Okay, a very subtle name change that we see there. So if we have a look here in terms of naming, the first one we have is calcium and oxygen, so it's going to become calcium oxide. Okay, that's oxygen there. This would be potassium bromide. You tend to write the second one also in lowercase, so just keep that in mind. We're going to go into these ones where we see that there is a different subscript number. So subscript number here are slightly different. You don't need to worry about the actual number when we're writing the names of ionic compounds. So this is just aluminium oxide. And we have magnesium chloride here. Okay, the reason why these numbers don't really affect it is because we already know what the charge numbers of magnesium and chlorine is, so we can actually already predict the formula regardless. The charge or the valency of magnesium is 2+, chlorine is 1-, and so as you can see in this formula here, effectively after you get rid of the plus and minus signs or minus signs, the numbers have swapped over with each other. That's what we get there. Okay, so the next bit is trying to write out the formula and also write out the name. Okay, so same idea here. What you might want to do is actually just write out the equation like so and compare to see if the numbers are any different. If the numbers are the same, just combine the symbols together. We get sodium bromide. If we have a slightly different number, let's say we use aluminium here, okay, aluminium 3+, and we get sulfur 2-. If they're different, get rid of the plus and minus signs and you swap them over to the opposite part, bottom parts of that equation or formula. So aluminium is aluminium 2, sulfur 3. We're going to call this aluminium sulfide. Again, like we said, because we know what the valency of the aluminium sulfur is, we don't need to specify if it's plus or 2 or whatever in the actual naming there. Okay. Right. And then obviously, as you noticed in the earlier components when we talked about the periodic table, we kind of glossed over what the transition metals are. Now, usually transition metals, okay, transition metals, the middle part of your periodic table, the valency is usually 2+. That's usually 2+. Okay? There are some exceptions to the rules. There are times this Ag, which is silver. Silver is always +1. Okay? And then we have something like gold. which could be +1 or +3. Okay, now for you, you might think, how do I know which one's which for these situations? They do actually tell you. Okay, so you can actually find it from the naming. So let's say lead 2. So something that says lead 2. If you ever see a name of an ionic compound that has sort of these Roman numerals in it, that 2 represents a loss of 2 electrons. Tin 4 means a loss of 4 electrons. So that's what you need to remember. Now, let's say for the example, we just write zinc chloride and nothing's specified for you. So no number provided. What do you do then? Well, the assumption is it's still 2 plus. Okay, so if it's not told to you what the transition metals Roman numeral is, you just assume it's 2 plus. Anything else, assume what the number tells you. So if it says iron 2, it's 2 plus, iron 3, it's 3 plus. Keep that in mind. Okay, so you can see here. You can also work backwards to work out what type of metal ion you use. So, for example, chlorine is always 1 minus. The fact that we need 2 chlorines to balance this out to 0, remember, because the compound has a net charge of 0, then the ion has to be 2 plus. For bromine, if you look at your periodic table, bromine is 1 minus, which means the lead that we're using has to be 4 plus in order to get 0. So you kind of work out your mass here. So we have 4, so 4 minus 1, 4 times minus 1 plus positive 4 equals to 0 there. So that's how you need to work it out. Okay, so here we need to work out the naming, so we'll use iron here. So we know that it's the same charge. Just combine the formula together, and we get iron 2 sulfide. We get iron 2 plus here, and nitrogen 3 minus, or nitride. We get iron 2, so that's still iron 2, and then you write nitride here. The formula would therefore be Fe, 3 comes to the bottom of iron, and then 2 goes to the bottom of nitrogen, as they're not balanced already. Okay, so Fe3N2. And so those are the other examples you can look into. Alright, if we're trying to find the correct name of each one of these, it's quite straightforward. So this 3 here will indicate what the ion is, remember, because if we see 2 different values, it means they've swapped over. So we're dealing with iron 3 sulfide. This one here you'll need to work out using the oxygen, because we know that oxygen will have, its valency will be constant. So we know that oxygen is 2 minus, which means that the copper here has to be 2 plus to make everything equal to 0. Okay, so C, or number 3, is the answer there. Alright, so the next bit we need to do is actually work out the complex compounds. So what we mean by complex compounds, things we call polyatomic. So anything that has multiples, so we have sulfate, something like sulfate, we have hydroxide. These ones obviously you can just search online what the names are for the polyatomics. And then we have carbonate, which is CO32 minus, and wondering if there's anything else. No. Okay. So for the polyatomics we have sodium. Sodium is +1. Carbonate is CO3 2 minus. Now what you need to appreciate here is the bottom number here of the carbonate can't change when you go through this combination, or when you're combining the equation together. So what you need to do is, same idea, this 2 will go down to the sodium, so it becomes sodium 2. This carbonate becomes carbon CO3. Another way some people might tend to write it is this. Okay, now obviously 1 is redundant, so we don't write it, so that's why I wrote it there. Now the reason why this 3 doesn't change is because carbonate, its formula is CO3. Now if I change that 3, I get a completely different chemical, and no longer am I writing sodium carbonate, maybe I'm writing sodium carbon dioxide or something like that. Okay, this one here, we have sodium and sulfate, as we see here, so it's called sodium sulfate. Names don't change, you just leave it as it is for the polyatomics. Carbon dioxide, this is actually going to covalent compounds, but you can see the di actually represents 2 oxygens, so that's 2. We'll leave these ones here because these aren't ionic compounds. We have copper oxide, so copper, so like we see here, copper is a transition metal, but it doesn't tell you what the valency is, so we assume it's 2. So copper is 2 plus, oxygen is 2 minus, so it's CO or CuO. We have calcium, and then we have carbonate there, so it is calcium carbonate. Okay, and that's what we have here. So we've gone through naming different types of ionic compounds, we've gone through the naming, we've gone through writing the formula, and we've also gone through writing out the names and the symbols for the polyatomic ions. So hopefully that helps you with the worksheet that you need to do. Anyways, thank you for listening to this video. Hopefully you found it useful.